and welcome to this lecture. This lecture is about one of the most celebrated results of probability theory. It's called the central limit theorem. Okay, you might have heard this somewhere, the bell-shaped curve and where it comes from and how the bell is everywhere. Everywhere you look at, you have this bell-shaped curve in the distribution, etc., etc. The central limit theorem is behind all of that. It's a very classic, celebrated result, and it's important in any probability course to understand it cleanly. And you will see this moment generating function that it describes sort of plays a central role. It ties up this very well. There is a little bit more of analytical wizardry involved there. We won't spend too much time on that, but I'll at least point out where this comes from. Okay, so it's a very powerful result. You will see finally when we want to look at the binomial distribution, right? We were looking at this probabilities of y deviating from its expected value, the binomial random variable deviating from its expected value. We had the Chebyshev bound, we saw the Chernoff bound. None of them were really close to the actual probability. You will see the central limit theorem will give you a very good approximation to the binomial particularly. Okay, so it's a very useful, powerful result. I'll make more remarks on what it means, etc. But let's jump into it. Okay. Okay, so let me define this moment generating function. I did refer to it before, we have seen it before, but I want to talk a little bit more about it and get started and in a slightly more formal fashion with the moment generating function. Okay, so let's start with the zero mean random variable. Once again, this is not a big issue. So supposing you have a random variable which is not zero mean, what do? You simply subtract the expected value, you get a zero mean. So you go to that, and then you know that translating doesn't change anything. Any event with the original one is simply translate. So it's all easy to go back and forth with this. Okay, so the MGF of x, it's denoted mx of lambda. I'll use this notation, mx of lambda. It's a function from the real numbers to real numbers. It says r to r here, so you can put a math bb here. I should change that. So it's from r to r, and it's defined as mx of lambda is expected value of e power lambda x. Now convince yourself that this is a function from the real numbers to real numbers. Okay, lambda is a real number, right? Given a real number lambda, particular value for lambda, 1, 2, 1.5, 3.5, pi squared, e squared, whatever the value of lambda is, it's a real number. I can just do expected value of e power lambda x. X is some distribution, but expected value of e power lambda x is going to give me a number. Okay, so this is a mapping from real numbers to real numbers. It's a function. Okay, so it has that nice looking form, expected value of e power lambda x. Okay, so now supposing x is discrete, it has a PMF fx, and you know the PMF. Okay, so usually we assume that. So basically x will take values small x1, small x2, so on. What is the probability it takes value small x1? Fx of x1. What's the probability it takes value x2? Fx of x2. So what is mx of lambda? It's expected value of e power lambda x. So it's e power lambda x1 times the probability that x takes value x1, which is fx of x1, plus e power lambda x2 times the probability that it takes the value x2, and so on. Okay. Very simple, isn't it? I mean, it looks a bit more complicated notation. When you actually break it down and look at what's going on, it's a very, very simple calculation. Now it turns out it can also be used for continuous distributions. Okay, so we have seen these continuous distributions before. When you have a density fx and some support tx, you can again define mx of lambda. It's just the expectation. Now except that the expectation is not summation anymore. You remember from discrete to continuous, when you go, the expectation becomes integration. You have to integrate over the range e power lambda x fx of lambda dx. Okay, over x you integrate. I made a mistake here. This is a huge mistake. Apologies for that. It's fx of x. Okay, it's not fx of lambda. Okay, sorry. So it's the density times e power lambda x dx. Okay, so if you want a picture, for this continuous thing, supposing this is your fx of x, you will have a e power lambda x, right? So e power lambda x, let's say lambda is positive. Okay, so e power lambda x. So you will multiply these two. So you multiply these two and integrate. Multiply and integrate. That's all. Okay, numerically there's nothing in this problem, right? So you have e power lambda x. For different lambda, you'll get different e power lambda x. Of course, if lambda is negative, it will go the other way, right? It will go this way. But it doesn't matter, fx of x stays the same. You just multiply these two functions and integrate. Okay. So it's very simple definition in some sense. If you have a numerical tool, you can do it. If you know enough integration, you can also get closed form expressions for these integrals and all that. We won't spend too much time on this, but I want you to know that the MGF is a simple calculation involving the exponential function, of course, but it's just an expectation calculation. Okay, so nothing to be very alarmed about. Let's see examples. Okay, examples are always very nice. So we'll start with the simplest possible example. Okay, in this case, it's a ridiculous distribution. I'm going to say x equals 0. I'm taking a random variable which takes only one value with probability 1. Okay, so if you look at mx of lambda, it just becomes 1, right? So it's 1 into e power 0. Well, lambda times 0, it's again 0. It's just 1. Okay, so easy enough. Seems very simple. You can also take other constants. If x is not 0, then of course expected value of x is not 0, right? So you have to pull it down to this, and you can try that. So that's why 0 is meaningful. Okay, so let's take this next distribution, which is sort of like Bernoulli P. Okay, so this is actually what? Centralized Bernoulli P. Do you agree? Centralized Bernoulli P, right? So what is Bernoulli P? Bernoulli is 0, 1, P 1 minus P, okay? Expected value equals P, okay? Now I'm going to subtract P from this, minus P, and you get minus P, 1 minus P, probability remains the same. That becomes centralized Bernoulli. Okay, so expected value is 0. Okay, so it's just a simple centralization. So you get minus p with probability 1 minus p and 1 minus p with probability p. So for p equals half is what we saw before, right? Minus half, half with probability half, half each. Okay, so if you do the moment generating function for this, you will again get 1 minus p times e power minus p lambda plus p times e power 1 minus p lambda. Okay, you can put p equals half. We will recover the previous result that we had for centralized Bernoulli half. Okay, so here is a slightly different random variable. Okay, so this is again a discrete random variable. It takes 3 different values: minus 1 with probability half, 0 with probability 1 by 4, and 2 with probability 1 by 4. You can check its expected value is 0. I've centralized it, sort of make sure that it works. Now, if you write down mx of lambda, it's going to be half times e power minus lambda plus 0.25 times e power lambda into 0, that becomes just 1, plus 0.25 times e power 2 lambda. Okay, I want to point out one thing. Just pause for a second. If I give you the distribution, you are able to go to the mx of lambda. If I give you an mx of lambda in this form, you can go back to the distribution, right? Think about this. Okay, right? So particularly with this e power lambda, e power minus lambda form, if I give you the distribution, you go to the mx of lambda. If I don't give you the distribution, if I give you the mx of lambda, you can also go back to the distribution. Okay, so it's very easy. So let me show you how that is done here. So here I've given you an mx of lambda, which is 1 by 3 e power 3 lambda by 2 plus 1 by 6 e power minus 3 lambda plus 1 by 8 e power minus lambda plus 1 by 8 e power lambda plus 1 by 8. Okay, this is the mx of lambda I have given to you. From here, you can almost read out 1 by 1 what value it takes. Notice this expression here, 1 by 6 e power minus 3 lambda actually gives you the distribution directly. You can just read off from every term here, you can read off one particular value that x takes. Okay, so notice this term here. Okay, 1 by 3 e power 3 lambda by 2. It means that x takes value 3 by 2. Okay, so this gives you x takes value 3 by 2 with probability 1 by 3, right? So this directly gives you this value, right? Remember this expected value of e power lambda x. So x takes value 3 by 2 with probability 1 by 3. Okay, you can go back to the formula. It is just the direct formula, right? So expected value of e power lambda x will be, plus xi, plus fx of xi times e power lambda xi, isn't it? So it will have a term like this, x takes, so this implies x takes value xi with probability fx of xi. right? So you can go from the distribution to the particular term of fmx of lambda, or you can take the particular term of mx of lambda and go to the distribution. That's what I'm doing here in reverse, okay? So this is an important idea, okay? The distribution fixes the moment generating function. The moment generating function also fixes the distribution. So from going from distribution to moment generating function is one-to-one, okay? So notice this one-to-one relationship. To describe a random variable x, you can either give the actual distribution or you can give its moment generating function. Both are one and the same, so they go back and forth, okay? It's an important thing to remember, okay? So you see here 3 by 2 with probability half. What about this guy? This term here, so maybe I'll use a different color. Okay, so you see this term here, this gives you this guy, right? X takes value minus 3 with probability 1 by 6. So likewise you can see every term, x takes value minus 1 with probability 1 by 8, x takes value 0 with probability 1 by 8. Did I get this right? I think this is wrong. Okay, now I know what mistake I made. This is not a valid distribution, so it turns out this needs to be 1 by 4. Thought I corrected it. Okay, so this will have to be 1 by 4 for this to be a valid distribution. Apologies for that. Okay, so this is correct. So you have minus 1 with probability 1 by 8 and 1 with probability 1 by 8 and 0 with probability 1 by 4. Notice this value is important to understand. So this gives you x taking value 0 with probability 1 by 4. Okay, so it's like e power lambda into 0. Okay, so you have to think of the 1 as being, you know, e power lambda into 0. So notice how the MGF directly gives you the distribution also. You can go from distribution to MGF or MGF to distribution. It's a one-to-one relationship. It's a useful thing, useful skill to build up and understand what's going on. And finally, if x is normal 0 sigma square, this is a very, very, very important result, extremely important. I've just put it as the last example. Let me put 5 stars next to it and 5 stars to the left of it to drive home the point that if there is one MGF that you have to mug up by heart and remember, it's the MGF of the normal distribution. Normal distribution with mean 0 and variance sigma squared, the MGF is e power lambda square sigma squared by 2. Okay, just mug it up by heart. If somebody wakes you up in the middle of the night and asks you, you should be able to say, okay, MGF of normal 0 mean variance sigma square is e power lambda square sigma squared by 2. Okay, very, very important to know this. So how do you prove this? I mean, it's not, so I'll leave it as an exercise. So it's basically minus infinity to infinity e power lambda x, right? And then you have this 1 by root 2 pi sigma e power minus x squared by 2 sigma squared dx. This guy you can show is actually equal to this. Okay, so this is an exercise in integration. It involves, you know, completing the square and the numerator and in the exponent and all that. And I don't want to go into the details here. This is an exercise for you. Look it up. If one of you, you know, can solve this, please post on the discourse forum a solution to how this came about, and everybody would appreciate that. Okay, so this is an exercise for you to do and post on the discourse forum. Okay, so this is examples. Hopefully this conveys to you how to work with MGFs. Generally discrete you see is very easy, but continuous is a little bit more involved, involves integration. I'm not going to expect that you know all these integration steps, but if you know, do share and let people also come out. What's important is the final result. The final result is really, really important. You should know that by heart. Okay, so why moment generating function? Where is that moment and generating and all that is coming from? Here's the reason for that. Okay, so you can expand e power lambda x as 1 plus lambda x plus lambda squared by 2 factorial x squared, etc., etc. Okay, both of these should give you the same function. I mean, I know I formally didn't define any random variable exponentiation and all that. We are not going to do all that. Just intuitively you can see why this has to be true, and that's good enough for us. Okay, so you see this is just the exponential e power x expansion. E power x is 1 plus x squared by 2 factorial x cubed by 3 factorial, so on. So that's the expansion I've done here. Okay, now expected value distributes inside summation, assuming convergences, etc., etc. All of that is going on. So expectation will go in, and expected value of 1 is just 1 plus lambda times expected value of x plus lambda squared by 2 factorial expected value of x squared, expected value of x cubed, so on, so on, so on. So expected value of e power lambda x, if you were to write it as an expression in terms of lambda, lambda squared, lambda cube and all that, the coefficients give you the moments. So these are called moments. This is the first moment or the mean. This is the, let me write it out properly, first moment. This is the second moment, so on. Okay. This is the third moment, and this is the MGF. So MGF is basically an expansion. If you expand the MGF as a polynomial series in lambda, then you get the first moment, second moment, third moment, and all that. Okay. So here's an example. Okay. So let's take this example. It's normal distribution, 0 mean variance sigma squared. The moment generating function is e power lambda square sigma squared by 2. Okay. So you expand on the left side, you get this expression. You expand on the right side, e power x is 1 plus x squared by 2 factorial. I am writing the x squared by 2 factorial in a different way here. This term is actually equal to lambda squared sigma squared by 2 whole squared by 2 factorial. It's the same as that. Okay. So I put a 3 there, this 2 squared will become 4. 3 in the numerator, 3 in the denominator will make it 4 factorial lambda power 4. Why am I doing lambda power 4 by 4 factorial? Only then it will look like the left hand side, right? So it will look exactly like the left hand side, and that's what I want. So once I have an expression like this, I can read off moments. Expected value of x is 0, expected value of x squared is sigma squared, right? It's just the coefficients, lambda squared by 2 factorial, the coefficient is expected value of x squared on the left hand side, sigma squared on the right hand side. Anytime you have equality like this, which is true for every lambda, okay, then you can read off the corresponding things. I mean, of course, convergence, so many things are involved here, but we'll assume all that. Okay, expected value of x cube is 0. Expected value of x power 4 is 3 times sigma power 4. Okay, a result that is not so difficult. It's a little bit more difficult to derive if you were just doing integration. Okay, so from the MGF you can do this, and you can just keep going on and on and on and on and on. Okay. So this is why it's called the moment generating function. This is not so important to us in this class, but this is the reason why it's called that. Okay. Okay. Now what's more important to us is the connection between MGF and sums of independent random variables. We already saw this before, right? When we did the Chernoff bound for the binomial case, this was very, very useful. Now let's generalize. Let's see how to do this. Okay. So let's say we have two random variables which are IID according to some distribution, and I'm defining the sum of those two random variables, y equals x1 plus x2, that's it. Okay. So let me start with one simple example, x being IID Bernoulli P. Okay. So here the moment generating function will work out as what I've shown there, 1 minus p times e power minus p lambda plus p times, so this is just the usual, I mean this is actually the centralized Bernoulli, isn't it? So this is, okay, so I should be careful here, so I should write centralized. Okay, so we're all doing centralized, so this is just minus p, 1 minus p with probability p and with probability 1 minus p, right? So that's the expression that we got here. And now my of lambda, okay, because this is IID, is going to be mx of lambda whole squared. Okay, so I can just take this guy and square it. Okay, so this is just the square of, so this is squared. So when you square, you get this expression, right? It's a squared plus b squared plus 2ab. That's what you get. And from here, you can read out the distribution. Okay. So I went from distribution to mx of lambda, and then I squared mx of lambda to get my of lambda, and from my of lambda, I can read out the distribution. Okay, so it's 1 minus p whole squared times e power minus 2p lambda. So it takes value of minus 2p with probability 1 minus p whole squared. Takes value 1 minus 2p with probability 2p into 1 minus p, and takes value 2 times 1 minus p with probability p squared. Okay, so this is a way to find the distribution of the sum of two random variables which are independent by using the moment generating function. Okay, so this is very important to understand. So we know that there is a tie-in between the MGF and the sum, but this is, I'm just showing you examples of how you can use MGF to actually find the distribution of the sum of two independent random variables, and it's very, very simple and direct. Okay, so here's another example. Okay, slightly more twisted example. It's not centralized Bernoulli anymore. Minus 1, 0, 2. You have this other complicated looking distribution. Mx of lambda is this. You just square it. You get my of lambda. From there you can read out the distribution. I'm not writing down the distribution, but from the my of lambda you can see it takes value minus 2 with probability 1 by 4, minus 1 with probability 1 by 4, 0 with probability 0.0625, 1 with probability 0.25, etc. So you can read out the value. So here is yet another distribution, which is a little bit more complicated. You remember I had this distribution before, 1 by 3, power 3 lambda by 2, plus 1 by 6 and all that. And then if you square it, you will get this my of lambda. So look at this ugly little expression here, but nevertheless you can read out every value. It takes value minus 6 with probability 1 by 36. It takes value minus 3 by 2 with probability 1 by 9. It takes value 0 with probability 3 by 32. So from the moment generating function, you can read out the probabilities very, very easily. Okay, seems simple enough for small cases, but its real power comes when you use it for large n.